This is a lesson on gas theory. Gas theory is based on the kinetic molecular theory, and there are certain postulates for this, and using these postulates you can build up many of the laws that we have, and that's one of the objectives. First, matter is made up of small particles that have mass. Matter is made from small particles, we call them atoms now, that have mass. The volume of these particles is incredibly small compared to the total volume. So the volume of the individual particle and the total too is incredibly small compared to the volume of the total volume of the whole. Particles are in constant random motion. Constant random motion. When they do collide with each other or with the sides of the container, they're perfectly elastic. Elastic, which means there is no energy lost when they collide. If it's a perfectly elastic collision, like with the basketball on the floor, if you let it go, it'll keep bouncing at the same height. So if you have a basketball and you drop it from 5 feet, it'll bounce up to 5 feet every time. Temperature is directly related to the kinetic energy. Are directly related to each other. That means as one goes up, the other goes down, and vice versa. And these particles exert no force on each other. Exert no force, no attractive force, no repelling force as you go along. Now these are simplifications, postulates or simplifications in science. In real life, they don't really match this exactly. There are some close approximations on stuff, but it's not exactly there. Let's talk about the temperature and kinetic energy are directly related. You can do an equation. I'm going to derive it for you. It's in the book. That the average kinetic energy of the particles is equal to 3/2 RT. That means if the kinetic energy goes up, the temperature goes up. This is a modification of the PV equals nRT, where things are substituted in. Another equation, I might do a homework problem using that. Another equation is that the average speed, U is the speed, average speed of the particles is 3RT over M, and M is the mass in kilograms per mole. U is the average speed of the particles in meters per second. M is the molar kilogram mass. It's the mass of the gas in kilograms per mole. They do this to get it into SI units, SI base units. Sample problem. If you have oxygen at negative 73.15 degrees Celsius, what is the average speed of a gas particle? So you're trying to find U. 3 R 0.08206. I told you this is going to show up over and over and over again. Times 200, which is the temperature in Kelvin, divided by the molar mass. Now, oxygen is 32 grams per mole, so you move over 3 places. 0.032 kilograms per mole. So 32 from the periodic table, move it over 3. And you come up with approximately 39 meters per second. So that's how fast an individual gas particle is traveling in the air. Oxygen particle is traveling in the air around you. Now, it's not going in a straight line because it's constantly bouncing around. The average distribution, and this is a graph that's going to be seen oftentimes, this is the number of particles, and this is, in this case, speed. Not all particles are traveling exactly the same speed. Some are practically zero, and then it goes up, and it comes back down. Now, if you're having an equal number of particles that's heavier at the same kinetic energy, it will be less. This is the heavier, this is the heavier, because they're all bunched up down. This would be the lighter one. It's more spread out. You can go faster. Okay. Using these postulates, you can explain some gas laws. In knowing that pressure is number of collisions of particles on the side of the container. Let's say we'll go over it in class. Using these postulates, you can do like pressure and volume. You can explain why when the volume goes up, the pressure goes down. Using the definition of pressures, collisions per second. So if you make the volume bigger, you have a volume of a container like this. If you double the volume, if the volume goes up, you double the volume, the surface area will increase, and that will decrease the number of collisions per square unit, so the pressure goes down. So this is an example of using the gas theories and the definition of pressure to do that. Diffusion and diffusion. Diffusion is the speed of a gas, or the rate of a gas, rate of a gas passing through another gas. Another gas. Example of this would be perfume. If you squirt some air freshener or perfume, eventually you'll get to you in the middle of the room as gas particles spread throughout. And how fast it goes, we're going to have an equation for that. Diffusion is the rate of a gas passing through a hole into a vacuum or less pressure. This is like helium balloons. If you have a helium balloon that's latex, there's little bitty holes when you blow up the balloon, and the helium leaks out overnight. So the rate of a gas passing through a hole is fusion, comparing one to another. The mathematical equation, the rate of gas 1 divided by the rate of gas 2, or if you take 1 over 2, that would be the diffusion rate or the fusion rate, is equal to the square root of the molar mass of gas 2, you flip them, square root of the molar mass of gas 1. So they're reversed. You just got to remember what you want to do for that. And the molar mass is off the periodic table. So helium has a molar mass of 4. Radon has a molar mass of 222. So the ratio of helium to radon, you reverse it. You can't do the square root over the same thing. 222 over 4. That turns out to be about 55, square root of 55, so it's going to be 7.6-ish or so. I don't have a calculator on me. And that's just a ratio of things. So it's the helium will travel 7.6 times faster than the radon travels. Okay, real versus ideal gases. An ideal gas follows in this book, 6 postulates perfectly. Most of the time at warmer temperatures and low pressure, like Earth's atmospheric pressure, most gases behave fairly close to what an ideal gas is. So most gases in most conditions fairly closely follow the kinetic molecular theory up above. Follow the kinetic molecular theory. There are some changes, but not too bad. But if the temperature is low and the pressure is high, under low temperature, high pressure conditions, real gases, the amount of volume compared to it, let's see, look at number 2, the volume is really close together, so that affects how much spraying a gas has, and the attractions, the perfectly elastic, no force in each other. This one right here and right here, those two start to fail when you get that. If they're really close together, if you pack them in and squeeze them together, if the temperature makes them move really slowly, then you'll get those factors, the springiness of gas and the attraction of the gases to each other. So there's an equation where you're going to adjust for it. The ideal gas equation is PV equals nRT. The ideal gas equation alters the pressure and the volume. The pressure, you have to add a factor, and that's squared. The A times the N, which is the number of moles divided by the volume, squared, that adjusts for the additional attractive force between the particles. And V minus NB is an adjustment for the volume of the gas particles, equals nRT. A and B are constants that are found experimentally, and it depends on what gas you have. Some gases are bigger, which means the volume factor is larger. Some gases are more polar, so that will affect the pressure more. For example, if you have some chlorine, and it's if you have 1 mole of chlorine at 150 Kelvin in 1 liter, what will be the pressure? Okay, now let's do the simplified version first and compare it to the adjusted version. The pressure is what we're trying to find. The volume is 1 conveniently. The number of moles is 1 conveniently. R 0.08206, and the temperature is 150. Do the math. The pressure is equal to 12.3 atmospheres. Okay, now what we're going to do is plug that in to this equation. Pressure is what we don't know, plus A, and looking up in a table of values, A has a value of 6.49 for chlorine, 1 mole over 1 liter squared. The volume is 1 minus N, which is 1, times the B value for chlorine, 0.0562, equals, now the nRT is going to be the same as over here, 12.3. This works out to be P plus 6.49 times 0.9438, 12.3. Doing the math, P is 6.54 atmospheres. So the pressure decreases by half underneath these conditions from what should be expected. And that's due to the attraction of the particles with each other. And that concludes this lesson on kinetic molecular theory and gas theory.